Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I want to say how much I admire the fortitude of all of you sitting through all of this enormous tidal wave of wisdom that you're hearing here. So let me pick up where we left off. Remember, I was talking about how to build highly concurrent objects. And I spent the first part of the lecture convincing you that linearizability is almost always the correctness property that you want. There are certainly times when you might want to deviate from this, and if I have time, I'll give you some examples of non-linearizable data structures that are still very interesting. But for now, I'm going to stick with the main strategy. So we talked about 5 patterns for writing highly concurrent data structures. We covered 3 of them. I'm going to give you a very quick review of the 3 gray strategies, just so that you remember what they are. And then we'll push ahead. I'll talk about the other 2 ways of doing business. Then we'll turn our attention from a very simple data structure like linked lists and look at stacks and queues and counters and other non-trivial data structures, applying the same kinds of approaches to those. So remember, the simplest way is coarse-grained synchronization, where you put a big one lock on everything. That obviously doesn't scale. The next approach is fine-grained synchronization, where we split an object into multiple components, and we put a lock on each component. And the basic idea is that you only lock the parts of the object that you need. And as we saw, this is much easier to say than to do correctly. Many subtle difficulties happen if you aren't very careful. Now, I should mention that even though the algorithms that I've shown here have proofs, that is, they have things called proofs and things called theorems, there has been very little work on, for example, automatic proofs or machine checkable proofs in this area. And this is an area that is crying out for this sort of thing, because the data structures are either finite or almost finite. And there's a history of papers that have been published that have bugs in them. So if you're looking for a research area, then proving that some of these things actually work is, I think, would be a very interesting thing to do. The next thing is optimistic synchronization, where you search without locking, and if you find it, you lock and check that what you found was what you saw really is what you found. If everything is okay, then you're done, and you found what you were looking for much faster than you would have had you been, what was the phrase, acquiescent? And otherwise, you suffer the penalty of having to do everything over again. And so usually this is cheaper than locking, but if there's high contention or if checking is too expensive, then this isn't a great idea. The next thing that we didn't do last time, but we'll do this time, is what we call lazy synchronization. And lazy synchronization is based on the observation that the most difficult part of many operations on objects is removing things. So observing things and adding things is relatively easy, but once you remove things, then things can get very complicated. And often the best way to deal with this is to split things into 2 parts. You lazily mark something as being logically removed without doing the work of actually removing it. And you tell everyone who finds this to pretend it's not there. You can't keep doing this because eventually your object will be filled with dead pieces. So you have to physically remove it, but you can postpone the hard work of physical removing until a time when it's convenient. Finally, the last approach we'll look at is lock-free synchronization, where we take the atomic parts of the code, which are normally done with locks, and we move them down into atomic machine instructions. And you can think of this as moving the Earth with a lever, because we often do a lot of work, and then we do one atomic machine instruction, and that changes everything. And this has the advantage that it's robust against all kinds of scheduler anomalies. So if you acquire a lock and then the operating system decides to send you on vacation, then the other threads that are running are going to have a problem because you've got the lock and you're not doing anything and they need to use the resource. Lock-free synchronization doesn't have this problem. Lock-free synchronization is highly robust against these kinds of scheduling issues. But in practice, it can often be complicated, and sometimes, not always, but sometimes it can have a high overhead. So the example that we use is a linked list, which is fairly simple but highly flexible and useful data structure. We're going to use a linked list to implement a set, where a set is just a mutable, unordered collection of items. Each value is either in the set or not in the set. There's no duplicates. You can add an item to the set, you can remove an item, or you can test for membership. So our set implementation, there will be some minor variations, but basically we keep everything in sorted order. We have a sentinel node with the minimal value and the maximal value, which are never manipulated. And we can use, those are convenient to avoid various minor complications in the code. The basic idea is fairly obvious. We add something or remove something by doing the same thing you would do in a sequential world, except that we need to make sure that it works in a concurrent world. Coarse-grained locking, you lock the entire thing. This has the disadvantage that it's not scalable. The advantage of coarse-grained locking is that if you don't expect much contention, then this is what you should do. You should optimize the parts of the code that need optimization and not try to use high-powered machinery where you don't need it. And particularly, coarse-grained locking is easy to do, but you may regret it later. At one point, the Solaris operating system had one lock on the entire kernel. And years after it was obvious that this was a huge performance problem, nobody changed it because everyone was afraid. Nobody actually understood how it worked. And since this was the flagship product of Sun Microsystems, they were extremely reluctant to release something where they weren't entirely sure that it worked. And this was a drag on Solaris for many years. It was eventually fixed. Fine-grained locking, as I mentioned before, is hard to do right in many cases. The example that we had was hand-over-hand locking, where instead of having a single lock on the entire list, we would put a lock on each node, on each piece. And this would have the property that you would lock a node, lock its successor, release the previous one, and then acquire the next one. This is hand-over-hand locking. And this has the advantage that it gives you more concurrency because threads can traverse the list simultaneously, provided they're looking at we saw, you have to be very careful. For example, when you're removing a node using hand-over-hand locking, if I'm not going to actually modify a node, there's no reason to lock it. But in fact, you do need to do this. And this is actually a fairly common pitfall when people program up this kind of data structure. So returning to my earlier theme, these algorithms are fairly simple, but proving that they're correct can be very subtle. And it's easy to fool yourself into thinking that the algorithm is correct when, in fact, there's a hidden bug. So this is better than coarse-grained locks. Because threads can traverse in parallel, But as a practical matter, every time you visit a node, you have to acquire and release a lock. And we can make lock acquisition and release fairly efficient, but it's still not, there's still a cost to it. And if we can engineer our data structures to minimize the amount of locking, then that's really, that's what we want to do. So the next thing that we looked at was optimistic synchronization, where we assume that whatever it is we're looking for is not the target of a concurrent thread. So here we search through the list without acquiring any locks. And here too, the more you know about it, the more frightening this prospect is, because I haven't said anything about memory models and other ways that things that can get you into trouble if you read the data without locking. But the basic idea is you search without locking. Everything you look at can be changed out from underneath you at any time without warning. You find the part of the list that you're interested in, you lock it, and then you check to make sure that what you caught is a kind of fish, the kind of fish you wanted. So here, for example, we want to add C. So we traverse the list without acquiring any locks. Then we lock both of the nodes. Once we lock the nodes, they can't be modified or deleted. And then we add the, holding the lock, we add the item that we want to add to the list. And as I pointed out, it isn't that simple, because after you lock, you have to make sure that what you locked is what you thought it was. And the conditions that you want can be slightly subtle. For example, one way you can get into trouble is you find the nodes that you want. Then you go to sleep, someone else comes along and deletes one of the nodes that you're working on. If you then naively wake up and add your node, then this doesn't work. And so what we have to do is, once you lock the nodes, you have to make sure that the first one is still reachable. And this is a non-local property. Basically means you have to traverse the list twice. And we're still not done, because you can still get into trouble if somebody else comes along and adds a node between the two that you're looking at. Then when you wake up, acquire the locks, and add your node, then you also have a problem. Yes?
So while you are holding the lock and sleeping on one thread, how can any other thread acquire that same lock?
So here, you don't hold the lock yet. I saw the two nodes, and I saw that they were good, and I'm about to get the lock, when suddenly, poof, I go to sleep. The red node comes in, locks, changes, unlocks, and then I wake up, and I don't know that anything has changed. And then I lock the nodes, and I assume that everything is okay. And so what that means is that you have to check, once you get the lock, the conditions that you have to check for are kind of subtle. And here, we just have the second thing we have to check for is that the first node still points to the second node. Okay, evaluation of this. Well, this is usually a substantial improvement over hand-over-hand locking, because we don't have to acquire as many locks. In hand-over-hand locking, we have to acquire, on average, we have to lock half the nodes in the list. Here, we just lock two nodes, no matter how big the set is. When we traverse the node, we don't acquire any locks. So I can traverse the node, and you can traverse the node, and we don't interfere with each other. The only time we interfere is on the specific nodes that we want to modify, and probably they're different. This idea of having a wait-free traversal where we don't acquire any locks is going to be important later on, so keep that in the back of your minds. So at least on paper, this has better performance and more concurrency than the hand-over-hand locking. But it does have the disadvantage that you have to traverse the list twice, and the contains method has to acquire locks. So traversing the list twice may or may not be a serious problem. If the list is small, then maybe it's still sitting in a lot of it is still sitting in your cache, so it's not too bad. But you can't count on it. the idea that searching the list means that you have to acquire locks is unattractive. So the optimistic is effective if scanning twice without locks is more efficient than scanning once with locks. And is that true? It probably depends on the context. The reason we don't like the contains acquiring locks is most of the time we expect that's all people will do. That is, most of the time when you build some kind of a container object, you're mostly searching it rather than adding or removing things. So the next thing that we're going to look at is the lazy list approach. So you can think of lazy as it's very much like optimistic, except we're going to make a few small changes and guarantee that we only have to scan the list once. We don't have to scan it twice the way optimistic did, but we're still only going to acquire 2 locks. And the contains operation never needs to lock anything. So this is substantially more attractive than any of the lists that we've shown you before, because we don't have to do all of this work to validate. And we can completely eliminate locks from the most common of our operations. And the key insight, as I've said several times, is that the problem that we have is that removing nodes always causes trouble. And the bugs and pitfalls that we've seen before usually involve one thread removing something out from underneath another thread that's trying to use it. And so if we can make removing items less complicated, then everything else will be much simpler. So the idea is that remove is going to scan the list exactly as before. It's going to lock the predecessor of the node that we want to remove and the node itself, just as before. But the actual removal is going to be split into 2 steps. The first one is a logical removal, where we set a flag on the data structure which says, I'm not here. Even if you see me, this flag says, I'm not here, ignore me. The second step, we're going to actually move the pointers around and physically remove the item from the list. Now, this sounds like a very simple, even minor change, but it turns out that it's going to have a pervasive effect on the structure and performance of the list. So in picture, we're going to add a flag. Green means that you're present in the list, and red means you're logically deleted. And I hope nobody's red-green colorblind. I've actually had people complain about that. So logical deletion means we switch the flag from green to red, and physical deletion means we swing the pointer just as before. So what happens when we do this? So all the methods scan through when we're searching for something, we just go right through the list, ignoring whether it's present or not. We just follow the references. So that means that we're scanning through nodes that have been both logically and physically deleted. But because we're careful not to recycle that memory, or let the garbage collector deal with this, it's always the case that even if we're looking at a node that has been physically removed from the list, if we keep following the next references, we'll get back onto the list. That's an important invariant. So this means, for example, that removing a node doesn't slow down scanning, because we don't care whether a node is locked or not. We just scan right through it. When we find the node that we want, we still have to acquire 2 locks. Now, for validation, we can skip the expensive part. Remember, in validation, we had this problem that we locked a node, but we don't know whether it's still there. Someone might have already deleted it. So we had to scan from the beginning again to see whether we could reach that node. Here, we don't have to do that. All we have to do is we take the predecessor, which we've locked, and we check that it's not marked. It's not logically deleted. We check the current node, and we check that it's not logically deleted. Then we check that the predecessor still points to the current node, which is exactly what we did before. And now we're done. So all our validation is now local. instead of having to reread the entire list, we just look at the 2 nodes that we've locked, and that's all that we need. Now, I'm not going to prove this is true, but it's a good exercise to look at that, to try that. So here's the here's a picture. So this node scans through, and now it locks. It finds the node. It's halfway between 2 nodes. Suddenly, the red thread shows up. It decides to remove B, and it checks. It acquires the lock and checks. Well, A isn't marked, so it's okay. A still points to B, so that's okay. And then it does a logical delete by setting the flag. And then it does a physical delete by swinging the pointer. So this is, again, much more efficient than the removal that we had before, because we don't need to rescan everything. These magical flags save us from having to do all that. Now, the green node is still scanning through, and it doesn't care, so it gets back. So I'm going to show you in the slides that'll be on the web page. I'll have a lot more code examples, but I'm not going to go through all of those here because I want to cover more material. Now, when I show you this code, I want you to look at it as if it were an impressionist painting, in the sense that don't focus on any of the details. You just drink in the entire picture. And I'll help you do that by annotating it. But don't worry about any particular line of code. So what we do is the validate method says, check that the predecessor is not logically deleted. Check that the current node isn't logically deleted. Check that one points to the other. And return the conjunction of those 3 conditions. So it's very, very simple. This is the business end of the remove method. So what it does is you acquire the locks and you validate. If you found what you're looking for, then do the logical remove. Do the physical remove by changing the pointers, and then return true. So the translating the pictures to a code here is really quite straightforward. Now, the interesting thing here is that contains doesn't need to acquire any locks. And this is, again, as I mentioned, a very important practical constraint, because it means that every time you search the set, you don't have to deal with expensive locks. So what do? We start at the beginning, and then we search the range of keys. And notice we don't acquire any locks. We just read right through. We don't check to see whether it's locked. We don't check to see whether it's logically deleted. We just keep going. And then when we find what we're looking for, we say, is this the key that I wanted? And is it not logically deleted? If that's true, then we found it. And we've done everything without acquiring any locks. Now, if I were you, I wouldn't just take my word for this, because there's all kinds of subtle things that are going on here. And proving that this is correct is actually quite an exercise. We have a paper where Tony Hoare is one of the co-authors, where we actually do this. So if Tony Hoare thinks that this sort of thing is worth proving, then we should all pay attention. But it's a very simple algorithm. You could explain the algorithm to high school students. Explaining why it's correct is somewhat more advanced. So summary, wait-free contains says that if you're not marked, the invariant is that if you're not marked, you're in the set. If you're marked or you're not reachable from the root, then you're not in the set. And this invariant is the basis for proving the correctness of these operations. So there's another kind of theme here, which is that add and remove acquire locks, but contains doesn't. So in the early days of data structures, people moved heaven and earth to try to eliminate all locks from all the operations, and ended up with fairly complicated and somewhat inefficient data structures. But if you say, well, we really only need to optimize the really common calls, and if by leaving locks on the relatively uncommon calls, we can greatly simplify and speed up the common calls, then that's a good deal. So as a practical matter, we're believers in mixing and matching different synchronization operations on different operations. So the good thing about this is contains doesn't lock. In fact, it's weight-free. If you're uncontended, then you don't need to read traverse. It's still optimistic, and it has the disadvantage of optimistic operations in that it doesn't work very well if your optimism was misplaced. So if you have a lot of contention and your validation fails, every time you lock these two items, it turns out that one of them was deleted or somebody inserted something in the middle, then all the work you did so far was wasted and you have to start over again. There's reason to believe that's quite rare, because if that happened a lot, then the level of contention would be so high that no possible algorithm would work well. It just means your system needs to be re-engineered to get rid of that level of contention. So as an engineering perspective, you want to deal with low and medium contention, because if you have high contention anywhere, then you should probably redesign things. So if the optimism is misplaced, this doesn't work. But this does have the same problem that all data structures that use mutual exclusion have, which is that if you acquire the lock and you're delayed, then everyone else is delayed. And you could say, well, how likely is it that I'm going to be delayed? Well, you could, for example, take a cache miss after you acquire the lock, and that would delay you for maybe 20, 30 machine cycles. You could take there's multiple levels of caches, and the lower the level of the cache miss, the greater the penalty. You could take a page fault, and that would delay you for thousands of cycles. The operating system could decide to deschedule your thread and run someone else, and that would delay you for millions. And most of the time, you have no control over this. So this is why in a lot of the theoretical distributed computing, people talk about processes crashing and failing. So in a real distributed system, processes do crash. You could say, well, why do we care about crashes and failures in a multi-core? It's not the case that I'm going to flip open my laptop and one of the cores emits a little plume of smoke and the others keep working. More likely what will happen is one of my threads will get swapped out. And the delay is so long that we have to treat it as if they crashed, because we're not willing to wait for it to come back. So this is why you hear talk about crashes and failures in in models of concurrent systems. Although actual crashes and failures don't really happen, logically they do. And it makes sense to treat these kinds of unexpected delays as crashes and failures. So this is the main drawback for any kind of lock-based data structure. So one thread enters a critical section, crashes, then everyone's stuck. And so you have to trust the scheduler doesn't do this, but the truth is schedulers do this. There are lots of proposals. For example, some operating systems allow you to tell the scheduler, I'm about to do something really critical. Please don't deschedule me for another few hundred machine instructions. And the operating system, if it decides you're not abusing this, may do this, or it may not. So the thing about lock-free data structures is they guarantee what we call minimal progress, which is that some thread always makes progress. Nobody ever starves. Some threads might starve, but there's never deadlock. So some thread always completes a method call. And you can say, well, what good is that? I'm really worried about starvation. The answer is that most of the time, starvation, while a theoretical possibility, doesn't really happen. The scheduler may be inept, but it's not evil. And it may delay you at awkward and inconvenient times, but it's not really out to get you. And the natural kind of variation in non-determinism means that you're pretty much guaranteed that all threads will eventually make progress, provided we can guarantee that some thread always makes progress. So as a practical matter, we often settle for minimal progress instead of requiring that every thread always make progress under every circumstance, which is typically more expensive. Those are typically called weight-free data structures. Okay, so what we're going to do is we're going to take the same design that we had before, and I'm going to eliminate the locks and replace it with a compare and set operation. And just as before, the description that I give you of this may or may not contain bugs. And so while I present this, you should be thinking, am I trying to do a hand is quicker than the eye kind of a presentation where I gloss over problems? So think about what could go wrong. Before we do that, I'll review for you what compare and set is. So compare and set is, it's called a compare exchange on Intel architectures. It's basically a machine instruction, but we can think of this as a method where there's a location in memory, and we have an expected value that we think is there. And we tell the hardware to take the expected value and compare it to the one that's actually there. And if they match, replace that with a value that I specified. So it says that if my speculation about what's in this memory is correct, then replace it with something else that I gave you. And return true. And if it turns out that the actual value of that memory was different from what I expected, then leave it alone and return false. And all of this is done atomically. Now, you can prove theorems that show that this is impossible to implement in a robust way using read and write operations, very similar to the FLP proof that Marcos gave you. So this has to be done in the hardware. But the good news is that every processor since 1972 or something provides either this functionality or equivalent functionality. So we have the ability to do this kind of atomic operation. I should mention that it's typically expensive because it has to go all the way through the memory hierarchy. So this isn't something you want to use lightly. You know, typically a compare and set is maybe 100 times slower than a read or a write, because you can't use all the fancy buffering schemes that people use for reads and writes. So here's a way to build a lock-free list. So think about this as what we're going to do is, instead of locking the data structures and then doing operations, we're going to do a compare and set to change the values. And if the compare and set fails, then we'll go back and try again. So as before, we're going to be lazy, and we have our little flag that says whether the item is present in the set. So here we're going to do logical removal. I'm going to set this bit. So now C is not logically present in the set, although the node that holds C is still physically present in the list. Then I'm going to use the compare and set to say if that reference is still pointing to C, then turn it around and point to C's successor. And the comparison and the change are done atomically, so I don't need a lock. So I guess that's fairly simple. Is anybody looking at this and feeling a little creeped out? Do you have a vague sense of impending doom looking at this? So remember, we had this problem when we did hand-over-hand locking. What happens if somebody deletes the node that you're working on? Well, the same thing can happen here. So here we did logical removal, and then before we get around to doing the physical removal, somebody comes along and adds another node in between C and E. Now this will succeed because the value of the next pointer that it finds is the one it expected. And so this will work. And then the physical removal works because the value of that node is also what we expected. And as you can see, D, which we think is in the node, is in the list, isn't there anymore. So here too, you need to be very careful about these things. The first thing you think of is almost always 90% correct. And if you're really, really clever and experienced, then it'll be 99% correct. But there's no substitute for sitting down and actually working out at least an informal proof that this sort of thing is correct. So the way we're going to deal with this is we're going to combine the flag and the next pointer into a single unit. And I've represented this symbolically by removing the black line here. And so this means that when I do the comparison for the concurrent set, I'm comparing two values, the value of the flag and the value of the pointer. So I'm making my atomic operation just a little bit bigger. And in fact, this is a theme that unfortunately I won't have time to get into much, that people have discovered that the bigger you make your atomic operations, the easier life is. And if you push that to an extreme, you get transactional memory, which Tim was talking about. But for now, we don't have, if we had transactional memory, then this could be a little bit simpler, but surprisingly not that much simpler if we want a lot of concurrency. So we combine the bit and the pointer. And so Java actually provides something that does this called an atomic markable reference. And so what we're going to do the comparison set of both these values together. So here we have the logical delete. We'll play the ominous music because we're leading back up to the danger zone. And so, so we set that bit. And now, when the other thread comes along and tries to insert the new item, its compare and swap will fail. Because even though the reference, the pointer value it found was what it expected to find a node that was logically not deleted. It expected to find a green flag, not a red flag. And because the comparison fails, the compare and swap will fail. And so this way we will have skirted disaster because it makes no sense to append something onto a node that's logically deleted. And so the physical removal, however, will be able to proceed without problem. And so the node that tried to do this insertion will then have to go back to the beginning and try again. You can optimize this so it may not have to go all the way to the very beginning. But that's another story. But by putting the bit and the reference into a single unit, we can avoid this difficulty. So again, we'll use, this is a very useful, this is such a useful pattern of being able to put a reference and a bit together that the Java libraries give you a prepackaged version of this. It allows you to change the reference and update the flag. You can set the flag independently and read each value independently and so on. So here we are. We're going to remove node C. So the first thing it does is it changes the pointer. It does the compare and swap to do the physical remove without locks. Now, just to check, if we have two adjacent removes, that's another place where we got into trouble last time. So each one does the logical remove. And now both of those values are logically gone, even though they're still physically present. And when each one tries to do the compare and swap, one of them will fail. And one of those nodes will be physically removed. The other one will still be there. And so a side effect of this is that you might encounter logically deleted nodes that are still there because our attempt to clean up failed. And the question is, what do we want to do with them? Well, the easiest thing to do is if you encounter a logically deleted node, finish the job and try to physically remove it. Interesting thing is you only need to try once. Because if you succeed, you removed it. If you failed, that means that someone else got in there first and removed it. So it's a relatively efficient operation. Right, so here we have the traversal, remember, is lock-free. So then we discover that there's a deleted node. We do our compare and swap and physically remove it. Just to show you that this isn't all academic posturing, we'll show you some actually at this time fairly old performance results done on Sun machines, probably maybe 10 years old by now. But the basic idea is pretty much the same. So here we have what we would consider a relatively realistic scenario. This is the number of threads. These are the number of operations per second, so higher is better. Coarse grain and fine grain locks basically have fairly poor performance, and they don't really scale. Lazy list and lock-free are roughly comparable. Here, lock-free does somewhat better than lazy, although the difference isn't huge. If we increase the number of modifications, then we have roughly the same, 50% reads, it's roughly the same picture. As here, we slice it the other way, and as the contains ratio goes up, you can see that the coarse grain and fine grain locks remain roughly constant, and the lock-free and lazy are roughly similar. Okay, so these are the 5 patterns: coarse grain lock, fine grain lock, optimistic, lazy, and lock-free. And what I'll do next is talk about how to apply these same patterns to more complicated data structures. So I think I'll start that, and then we'll take a break in about 10 minutes. So I'm going to talk about concurrent stacks and queues. I chose these data structures for a couple reasons. One is that queues and their relatives are very useful. I understand that a number of well-known operating systems use lock-free queues for ready queues and scheduling. Stacks are interesting because you would think that stacks are inherently sequential. That if you push something onto a stack, you pop something, how could you possibly make that parallel? What I want to show you is that, surprisingly, stacks can be made very parallel. The greater theme being that often things that naively appear to be inherently sequential can be parallelized if you think about it in the right way. So once again, these are the different ways that we will consider building these data structures. So a little bit of terminology. So you can think of queues and stacks as having pools of items. So represent these things as, I don't know what you call it. At the hotel, they serve these for breakfast right next to the idli. What's it called? Yeah. I mean, in the U.S., I tell people they're donuts, but we want to be culturally appropriate here. So we have a collection of these things. And a queue has the property, of course, that when you remove something, what you get is the first in, first out. And a stack goes the other way, that the last thing that was put in the pool is the first one out. They can be bounded, which means that they only hold a fixed number of these items. That can be useful if you're, for example, buffering things and you want to make sure that one process doesn't get too far ahead of the other. Then you can put a limit on how many things can be buffered between them. Or you could have unlimited capacity. which is useful in situations where you don't want to worry about how many things you have in your container. What happens when you try to take something from an empty stack or queue? Well, one possibility is you can block, which means that you just wait until something shows up. The other place you might block is if it's already full. If it's bounded and full and you want to put something in, then you could block. The alternative is you could get back an exception. And each of these is useful under a different context. So we're not going to look at the cross product of all of these things because that would take too long. But instead, we'll look at a bounded blocking lock-based queue and a bounded non-blocking lock-free queue. For stacks, we'll look at unbounded non-blocking lock-free, and then we'll look at what we call the elimination backoff algorithm, which is a way of making stacks highly concurrent. So when we have a queue, there are a number of inherent challenges that we need to face. So what we would like is that if we imagine we have an N-queuer and a D-queuer, if the queue is big enough and the head and the tail are far enough apart, we would like them to be able to work concurrently without having to synchronize with each other, except possibly in some transient way. But if you think about it logically, if the ends of the queue are far enough apart, then there's no reason that these two have to communicate with each other because they don't influence one another. But if the queue is empty or full, then some kind of synchronization is necessary. So we want to, so really static structures aren't going to work because we don't want to force them to synchronize on every operation. They only have to synchronize when necessary. So here's one way to do a bounded queue. So I'm going to have one field which is a head, which points to a node that contains an item. We'll use a ball instead of a torus. And this is a dummy item. So the gray ball is like a sentinel. It doesn't mean anything, but it's there to make the program structure easier to understand. So right now the queue is empty because the head and the tail both point to nothing. So now when we want to enqueue something, what we'll do is we leave the head pointing here. We have the tail points to the new item, and that's the first item that is actually in the queue. So in order to make synchronization work, we'll have one lock that when you acquire it, it locks out all other DQ calls. So when I acquire that lock, an NQ might still be able to happen, but no other thread can do a DQ. And I'll have a symmetric lock that I'll use to lock out other NQs. So in this way, at least in principle, NQs and DQs can go on concurrently because they're using different distinct locks. Now, we need to tell whether the queue is full or empty because this is a bounded queue. We're going to put a limit on how many things you're allowed to put into it, and you always need to know whether a queue is empty. So I'll put a size counter. And in this example, we'll say the queue holds a maximum of 8 items. And the thing about this counter is it's incremented by NQ because the number of items is going up. It's decremented by a DQ. So here comes an NQer, which wants to insert this item in the queue. And so what it does is it locks the NQ lock, because after all, it's NQing. It reads the size, and I'll tell you what it's worried that the queue might be full. And I'll tell you in a minute what it does if it finds that the queue is full. But here it sees that the queue isn't full. There are fewer than 8 items in there. And so it doesn't need to lock anything. So it creates a node to hold it, and it makes 2 steps. It puts the item onto this linked list, and it updates tail to point directly to the last item. Then it increments it atomically, get an increment means atomically increment this value. And the reason this has to be an atomic increment and not just a regular increment is because there might be dequeuers running around who are also modifying this counter. So the lock doesn't protect the counter. So one pitfall of using locks is that the connection between locks and the data is a matter of convention. And you have to be careful that you understand that convention. Then you release the lock and go about your business. So suppose the queue was empty. So then the enqueuer notifies the waiting dequeuers. And I'll tell you how that works in more detail. But what it says is that if the queue was empty, then there may be dequeuers that were sleeping, waiting to get in. And so the enqueuer will go and wake them up and say, "Hey, come on out. There's something for you." Okay, let's roll the film back. And suppose that the enqueuer acquires the lock and then discovers the queue is full. So it sees that the size is too high. So then what happens is it will go to sleep. It'll release the lock and go to sleep. And again, when we talk about monitor locks, I'll explain in more detail what happens. A dequeuer here comes along and it acquires the dequeue lock, which guarantees that no other thread can do a dequeue at the same time. It's not going to inhibit other enqueues. So then it goes to the head, it goes to the sentinel, it reads the sentinel's next field. Then it reads the value that it's going to return, makes a copy of it. And then what it does is it makes the prior first node the new sentinel. Why do we do it this way? Well, when we talk about a lock-free version, this will be handy. But the convention is that the very first node in the list is a sentinel. It might have formerly been meaningful, but because it's first, it turns gray and it doesn't mean anything. Then decrements the size, releases the dequeue lock. If the dequeuer is unsuccessful, then it reads the sentinel's next field. It sees that there's nothing there, and then it goes to sleep. Now, you might say, well, what is all this business about going to sleep and notifying and so on? So I'm going to take this discussion of stacks and push it down on the logical stack and give you a very brief review of monitor locks and conditions. This may already be familiar to some of you, but I think it's good to make sure that this is loaded in your brains for when we discuss some matters. So this is all of interest to people who care about Java. But the basic idea is that when you can't get a lock, there are two things you can do. You can spin, which means you sit there and, as Lorenzo would say, you pester the lock, and you keep asking it. Sometimes, if you expect things to be short, then that makes sense. If you have no idea when that lock is going to become free or when the condition you're interested in is going to become true, then it makes sense to tell the operating system, I can't get anything done. Why don't you run someone else for a while? And we call that blocking. But we want to have a mechanism where if the condition you're waiting for becomes true, then someone will wake you up. And that's what we want to talk about. And typically, this is all rolled up in locks. So you can acquire a lock, you can release a lock, or you can wait on a condition associated with the lock. So in Java, there's a call to create a lock. There's a call to release a lock. There are calls that say, get me the lock, but don't try too hard. If I can't get the lock immediately, then return false. If I can't get the lock within a certain amount of time, return false. And the one that we care about now is that we want to create a condition to wait on. So what is a condition? Is when you call a wait that says release the lock and wait on release the lock associated with this condition, and wait until it becomes true. Signal says wake up one thread that's waiting on this condition. Signal all says wake up every thread that's waiting on this condition. So await releases the lock associated with the condition, sleeps, that is, it gives up the processor. At some point, it awakens, that is, it resumes running, and reacquires the lock and returns. So you execute down here, you're holding the lock. You say await. While you're inside here, you could release the lock and things can change. But when you return from this call, you have the lock again. Signal, again, awakens one waiting thread, which will reacquire the lock. Signal all wakes them all up. Let me give you a kind of a figurative view of how this works. So here we have the lock. This is the critical section. This is the code. In this case, we have an item that's sitting inside the queue. You can think of this as a room where the thread comes in and either deposits an item or removes the item. This is the waiting room where you hang out if whatever it is that you want if your current need cannot be satisfied. So thread comes in, it acquires the lock, and it goes into the critical section. It consumes the item, releases the lock, and goes on its way. So this is normally what happens. Now it comes back again for more. It wants to do a DQ. It acquires the lock. It goes in the critical section, and it sees, oh, it's empty. And now what? Well, you might say, well, okay, all I need to do is just sit around and wait for something to show up. Any reason not to do that? Because you're holding the lock. You know, it's like a 2-year-old locks the door and goes in the bathroom, locks the door, and then falls asleep. Nobody can get in there. So even if tons of threads want to deposit an item, they won't get in. Okay, so then it calls await, which we just talked about. And so that releases the lock and moves the thread into the waiting room where it sleeps. So now this thread is not using up any resources. It's sitting on some linked list in the bowels of the operating system waiting to be awoken. Kind of like that Prometheus movie. So another thread comes along. It acquires the lock, and it meets a similar fate. So it calls await, and now it's sitting in the waiting room, and they're both sleeping. Finally, an enqueuer comes along with an item to deposit. So it acquires the lock, goes in, deposits the item, and it calls signal all to wake up everyone. So they wake up. Now, they can't do anything until the orange thread releases the lock. But after it releases the lock, they've been woken up. Now, the specification, these specifications are all written very carefully by lawyers, and there's no guarantee on when actually you wake up. At some point after signal is called, at some point after the lock is released, then you wake up. And the red thread wakes up first, and it acquires the lock. Now, notice that when you wake up and reacquire the lock, there's no guarantee that there's anything there, because somebody could have gotten in there and consumed that item first. So the red thread, though, is lucky. It gets what it wants. The green thread wakes up. It acquires the lock. It enters and finds, oh, it's still empty. So then it has to go back to the waiting room. It sort of skulks back to the waiting room, goes back to sleep, and waits for better days. So this is, Java provides a synchronized method, which actually does all of this with slightly different keywords. But I'm going to skip that since Java isn't the point of this. Well, the last thing I want to do before we do a break is to point out yet another pitfall. So I don't want to give you the impression that all of this is easy. So here we have a situation where, thinking back on the last execution, where we woke up 2 threads and there was only one thread that could acquire something, say, well, instead of waking up everyone, why don't we just wake up one thread? That seems more economical. So here, same thing. Orange locks, deposits its item. Sees the queue is empty, so it signals, and it only wakes up one thread. Now a yellow thread comes along, and before the red thread can wake up, the yellow thread comes in and deposits something, acquires the lock, and it says, well, the queue is not empty, so there's no need to signal, right? Because the only reason that threads would be sleeping is because there wasn't anything to consume. If I'm the first one to put something in, then there might be sleeping threads. But if I come along and there's already an item there, then there's no reason to wake anyone up. So it unlocks and goes away. The red thread wakes up. It comes along, it consumes its item. It goes on its way. And now there's nobody left to wake up the green thread. Because it's waking up only one thread was a false economy. Because the way things were set up, that green thread is going to wait forever, even though there is something for it to do. And so what's wrong here is that we were too parsimonious with our wake-ups. And so what I advise my students is always use signal all and notify all, even if you think you can prove it's unnecessary. Because sooner or later, somebody's going to come along and change your code, and they won't think about it. And lost wake-up bugs are very hard to find because nothing happens. So it's a sin of omission rather than a sin of commission. And what will happen is you'll have a thread that waits forever with nothing to do, and it can take a long time before you notice this. Okay, let's take a break and come back in 5 minutes. Okay, so we can do a kind of an engineering review. So the NQ and DQ methods don't share locks. So that means NQs and DQs can go on in parallel. But they do share an atomic counter, which is accessed by every method call. And you could say, well, we've removed one synchronization bottleneck only to encounter another one. And so I'll give you just a brief description of what you can do to alleviate this. This is more amusement than anything else. So notice that the counter, the NQ method only increments the counter. And the only thing, it doesn't care what the value is, it only wants to know whether the queue is already full. Symmetrically, the DQ method only decrements the counter, and so it only cares whether the value is 0. Any intermediate value is of no interest. So what we can do is we can split the counter into two pieces, which we'll call the NQ size and the DQ size. And then we'll have the NQer increment one counter, the DQer decrements the other counter. When the NQer runs out of room, then we stop and lock both of them and transfer the credits from one side to the other. And that way we can greatly reduce the amount of locking and synchronization that we have to do. And depending on your taste, this is either a biohack or an elegant solution to a synchronization problem. And you can take your choice. Okay, so let's make this lock-free. That is, we're going to replace the locks with a compare and swap. So as before, we'll set everything up pretty much the way it was before, with the head and the tail and the sentinel. And remember, the compare and swap operation allows us to atomically change a field. It says, if this field is what we expect, then set it to the value that I give you. And so here we have an NQer that comes in, and it creates a node to hold the item. And then it does a logical NQ, which is a compare and swap, to swing this pointer. And so now we're in a kind of a curious halfway state, because the item is reachable from the head, but the tail is off by 1. And because I'm assuming we don't have transactional memory, we can't change the head and the tail simultaneously. So we have to split this operation up into 2 atomic steps. So then we do the physical NQ, where we'll do a compare and swap to set the tail to point to the tail field to point to the new and actual tail. Now let me emphasize that these 2 steps aren't atomic. And so now we have to be prepared whenever we look at the tail to find either that it's good and points to the tail, or it's off by 1. And it's looking not at the last node, but at the node before the last node. And so what do you do if you find a trailing tail? Well, it's like the logical delete that we saw before. Probably the best thing to do is to stop and fix it and then resume. And this guarantees that the tail never falls very far behind. In fact, it never falls more than 1 away from the actual tail. What happens if your compare and swap fails? Meaning, I did a compare and swap, and behold, what I find is different from what I expected. So if you're doing a logical NQ, that means that you're in trouble. That means that somebody else NQ'd something or DQ'd something, and the best thing to do is to just give up and start over again. If you're cleaning up on behalf of yourself or someone else, then actually that's okay, because it just means that somebody else did the cleanup for you, and then you can proceed. What does a DQer do? Well, the DQer reads the value that it wants to DQ, and then it does a compare and swap to make the first node the new sentinel. So this is one reason why having a sentinel is a good idea, because if we didn't have that sentinel, this would be much, much harder. But because we have the convention that the physically first node contains a meaningless value, we can do this. So the next thing we want to say is, well, when we're putting things into the queue, we allocate a list entry to hold it. When we remove something, we remove a list entry. And what do we do with these things? So we have an ecological problem in that we're allocating all these list elements and only using them once. Now in Java, of course, where there's garbage collection, this isn't much of a problem because we'll let the garbage collector deal with it. But what if we're writing in a language that doesn't have a garbage collector? Or what if we don't want to use the garbage collector because we think we can do it more efficiently? So here, for example, the DQer DQs something, and it should be able to recycle that node. Now, we have to be careful here. So let's say that each thread has a free list of unused queue nodes. Local stuff is better. Anything we do without synchronization is better. So everybody keeps their own free list. And you can allocate and free from your own list. And if you run out of things, then we have some extraordinary way of allocating a new storage. But what we would like is that everybody allocates and frees from their own list. Now, this sounds like a very simple idea, but it's fraught with danger. And so here is another way that you can get into a trouble. So here I have a node that is about to do a compare and swap. So this is the value it wants to change. This is the value it wants to point to. This is the head and tail part of the queue. And this is the thread's free pool. So what it wants to do is it wants to, it's in the middle of a DQ, and it wants to take this reference and set it over here. So it wants to redirect the head from the gray node to the red node. But before it does that, it falls asleep and takes a nap. Now, what happens is all kinds of other threads come along, and they do lots of DQs and move these items into the free pool because they've both been DQ'd while this thread is off on vacation. And currently, this is what the queue looks like. It's empty. This is a sentinel node. And while this thread is still sleeping, these nodes are reused. And so now what happens is that one of the nodes that was in the free pool is placed back in the queue, holding a different item this time, but the address is the same. And now the thread wakes up and says, oh, where was I? Oh, yes, I was about to do a compare and swap. And it does the compare and swap, and in fact it succeeds because the pointer value that it presents is actually the one that it expected. What it doesn't know is that the meaning of the data that it points to has changed because we recycled the data. The physical location is the same as what it expected, but the contents have changed unexpectedly. And so now the queue is a complete mess because the head points into the free pool and so on. So this ecologically responsible green idea, which seemed so virtuous, turned out, like so many ideas of the kind, to lead only to more trouble. So what went wrong? At the beginning, this is called the ABA problem. And you see this a lot in concurrent data structures. The head reference here is value A, and the thread reads value A. Later on, the head reference has value B, and node A is freed. And while it's freed, its meaning changes. Its contents change. And then it's set back to A, and then compare and swap succeeds because the references match, even though this node has been reincarnated to have a different meaning. And this is a common pitfall if you're using compare and swap, combination of compare and swap and memory management. So why is this? Well, this happens with compare and swap, and this is built into the architectures. There's another roughly equivalent thing called load link store conditional that the PowerPC provides that doesn't have this problem, which makes your life easier. But since most of us are doomed to use Intel machines, we have to worry about compare and swap. So one solution is you could tag each pointer with a counter. And every time you recycle that data, you increment the counter. So the pair of counter and reference are unique, even if the reference is the same. And you can say, well, what happens if the counter overflows? Well, like every overflow problem, maybe it won't overflow in your lifetime. You don't have to worry about it. Maybe it will. Depends on the context. This is a common enough pattern that, again, Java provides something called the atomic stamped reference class to solve this problem. If you want to implement this in language other than Java, then the usual ways you can take a word, and usually the low-order bits on an address aren't used, and you can use that as a counter. And you can't do that in garbage-collected languages because they don't like it when you play games with their pointers. Okay, so let's switch our attention from queues to stacks. So a stack is just like a queue, except that we move we call the operations push and pop, and push and pop operate on the same ends of the object instead of at different ends. So here's a very simple lock-free stack. So we have a pointer to the top of the stack. We have a sentinel node, just as before. So when I want to push, I create a new node. I set the reference to point to the sentinel. And now I do a compare and swap. And now my node is at the top. So I can do another push. Now I want to do a pop. What I do is I read the value that I want to pop, and I do a compare and swap to push it back. So this is very simple. If we don't do memory recycling, we don't need to worry about ABA. If we do, then we can solve it with by attaching counters and so on. What's good about this is there's no locking. But the problem, well, again, if we don't have garbage collection, then you have to watch out for ABA. But the problem is that everybody who wants to operate on the stack, whether they want to push or pop or anything else, they've got to do a compare and swap on the same memory location. And this is going to be a big, what's called a hotspot, because it's going to bounce around caches all over the place. If I'm pushing and you're popping, then it's going to bounce back and forth between our caches, and we'll take a cache miss each time we touch it, and the result will be dreadful. And in any case, there's no parallelism in the sense that if I want to do a push and someone else wants to do a push, and we collide, then it's kind of like one of those old-fashioned westerns. One lives and the other one dies. It's a showdown, and there's no way that both of them can make progress at the same time. So the operations are effectively serialized. So there's really no concurrency going on here, even the pushes and the pops. have no concurrency. And you might say, well, this is the way that it was fated to be, because how can you possibly get concurrency out of a stack where everything happens all at once in the same place? So what I'm going to tell you is how to take contention and turn it into parallelism. So this is going to have the paradoxical effect that the more contention you have, the more parallelism you have, which is probably not what you were expecting. So often in many situations when you have contention, one way to alleviate it is what's called exponential backoff. So you're standing at a party in a group of people, and several people start talking at once. So what you do typically is you fall silent, you wait for a random duration, and try again. And if the durations are sufficiently spread out, then everybody gets to talk in a turn, and we don't have to worry about contention. So what we're going to do is we're going to take this exponential backoff idea and change it in some interesting ways. So here is the basic idea. We have a linearizable stack here. We have a thread that wants to do a push and a thread that wants to do a pop. So here the push happens, and now the pop happens. And what do we notice? It's the same at the beginning and at the end. So if the push and the pop kind of cancel each other out. So after an equal number of pushes and pops, the stack is the same. So this is a little bit like, if you want to sell your house, then you have to pay money to a real estate agent. But if you know that a friend of yours wants to buy a house, then you can do the sale directly without going through the real estate agent. So what we can do is we'll put an intermediate level in here, which we'll call the elimination array. And the idea is that when the pushing thread wants to push, it picks a slot at random, and it puts its value there. And the popping thread, when it comes along, it picks a slot at random, and it checks, is there something there for me? And if they happen to collide, then what happens is that the push and the pop can exchange their value without ever visiting the array, without ever having to do a compare and swap on the same location. So they can bypass all of the synchronization necessary. And then they continue, and the actual stack is left undisturbed. So there's no need to access the stack, and everyone is happy. Now suppose they're less fortunate, and they don't meet up. Then after a while, they can try something and say, they can try this. It's not working out, then they can go on to the stack. So this is kind of you try once to see whether you can do elimination. And if it succeeds, then you run off and don't bother with any synchronization. If it fails, then you go ahead and do the compare and swap part as before. And so the basic idea is that you can go to the lock-free stack and try it once. Try a compare and swap. If it succeeds, you're done. If it fails, that means that there's contention. And if there's contention, then it makes sense to, instead of backing off, what you might do is you might back off and say, well, I'm going to wait till the traffic clears out and try again. But instead of doing that, while you're waiting, go to the elimination array. Pick a random slot and try to have a rendezvous with someone else. And you're no worse off than you would have been doing the back off, because you wouldn't have been doing anything else anyway. And so this gives you a chance to short circuit all the synchronization. And it has the property that the higher the contention, the higher the probability you'll meet someone. So in this case, we turn the contention into concurrency here. So the way this works is we try the compare and swap. If it fails, we back off. There are a lot of parameters here. You can pick a random range and maximum weight type depending on the amount of contention. So if you keep encountering contention, so if you hang out in the array for a while and nothing happens, you try again and there's still contention, then maybe you want to narrow the range to increase your probability. But if there's contention on this structure, then maybe you want to use more slots. And an interesting open question is how to pick the waiting time and the size. I've seen proposals for using machine learning to look at similar kinds of problems. So doing some kind of intelligent learning on this kind of problem could be interesting. Yeah. I'll tell you in a second. If one push and one pop connect, the pushes and pops have to be one-to-one. So you have to make sure that if I push something, then it isn't popped twice. Yeah. That's a very good question, and I'll answer that. The key is, you remember I spent the very beginning talking about linearizability. And so if you have two pushes that happen close enough together, then they overlap. And the fact that one might physically, in the implementation, get to the array first doesn't matter, because linearizability says that if they overlap, you can order them any way you want. So this is why I spent all the time on linearizability at the beginning, is because once we realize that that's our correctness condition, we have a lot of freedom to do small maneuvers and things.
Suppose that the same node pushes and goes on the, in the buffer, in the intermediate buffer, and then that same node pushes the second time.
He won't push until he knows that it's been consumed if he's in the buffer. I have, in the longer version, I have the code where we go through that in more detail. But I'll talk about exchangers next and explain why that can't happen. But it's a good point. So we can choose larger ranges and longer times, and figuring out what the right values for these things are is, I think, an interesting open research question. Right now, every time somebody wants to show that this works well, they experiment a little bit, find the optimal values, and show how great it is. And if you have an alternative, then you pick less than optimal values and show how much better your alternative is. So how do we know this is linearizable? So there's an excellent question. Why should you believe me? Because these things are subtle enough that I could probably stand up here and present a totally bogus algorithm. And as long as I looked everyone in the eye and you would believe me. So let me outline how you would argue that this happens. So the basic idea is that I think the unlinearized, or rather without elimination, the one that just uses compare and swap, that's pretty clearly linearizable because it's just the order of the compare and swaps. So if the calls aren't eliminated, we just rely on that. So what happens is if we eliminate the calls, we're going to linearize each pop immediately after the matching push. And the combination, I claim, is a linearizable stack. So it looks something like this. So we look at the uneliminated operations, and we can linearize those in the order of the compare and swaps. So that's OK. So now we're going to look at the eliminated operations. So here's a push, and here's a pop. And let's say that they rendezvous in the elimination array. They never make it to the stack. So what I'll do is I'll find the point where they collide, the point where the pop thread discovers that there's an item waiting for it in the array. And so I'm going to schedule the push happens. The pop happens here when the popping thread consumes it. So I'm going to say, well, I'm going to put the pushing thread immediately before it, which I can do because it's clearly the push doesn't return until it knows that its value has been consumed. And I have all this freedom to pick a linearization point. And this is why we care about linearizability, because we need to be able to do these kinds of arguments to detect whether our algorithm is correct or not. And that's the basic argument. So the backoff, is good for two reasons. One is because we back off on the array, that cuts down the contention on the compare and swap. So that says that if you fail to connect with someone on the elimination array and you have to do the compare and swap, you're better off because we've eliminated at least some contention for this. So even if you don't ride the metro and you drive a car, you're better off if other people ride the metro because there's more room on the road for you. And elimination on the array cuts down the number of threads accessing the lock-free stack. And as I mentioned, the higher the contention, the higher the probability you'll be able to combine and use this shortcut. So this is a case where contention, we're turning something bad, namely contention, into something good, namely concurrency. So how do we implement this? Well, we need something called an exchanger, which is a way of atomically making sure that that the pushing thread and the popping thread both agree that they've handed over the item from the pushing thread to the popping thread. I think I'll skip some of this Java stuff, but an exchanger has basically three steps. Think of it as a box where I have a box, I put something into it, and then I wait. And someone else comes along, and they atomically replace my item with their item, and then they go about their way, and then we both are happy with what we have. It's a little bit similar to what Lorenzo was talking about, except we're not worried about Byzantine or rational processes. The other thing that can happen is I can go out there and put something in the box and wait for someone to show up, and they don't show up. So at that point, I can withdraw my offer. And you need to be careful that I don't try to withdraw my offer at the exact same time when someone else tries to accept it. So the status of an exchanger could be that the box is empty. It could be that one thread has put its item in the box and is waiting for someone else to come along and do the exchange. Or it could be that I want to use the box, but two other threads are using it already, so I can't. So this is the exchanger takes, so I want to do an exchange, I give the item, and I give it a timeout because I'm not willing to wait forever. So what I'll do is I'll loop until timeout. I think I'll just stick with the picture. So here is the exchanger. Thread comes along. It does a compare and swap and sets the state to waiting. So this says that the red thread has deposited the red item and is waiting for. Now this item could either, if red is pushing, then that's a real item. If red is popping, then this is a dummy item. You know, it's something that just says that I want to pop a value. So it waits for a while. And then finally, maybe another thread shows up. So what that thread does is it tries to exchange the item and set the status to busy. So using a compare and swap, it has to be able to change both fields atomically. It exchanges. And now it has the red item, and the blue item is waiting. And then at some point, red notices that something is there, and so it consumes the item and sets the value to empty. So that's basically how the exchanger works. I'm going to skip through the actual code here. Yes?
So you mentioned that you have to be careful with the timeout.
Yeah. So when you time out, then you have to do a compare and swap. And see if I can find that. Maybe I won't look for it. But basically, you try to do a compare and swap. If that fails, then that can only fail because somebody came along and actually did the exchange at the last minute. So all the state changes have to be done atomically using compare and swap. Again, with transactional memory, this would be a lot simpler because a lot of this depends on the fact that there's only one word can be changed atomically. But even transactional memory wouldn't make this too much simpler because the logic is the same in any case. Okay, so then how do we? So now that you've seen how to use the elimination array, I can show you the code for this visit method visits the elimination array for a fixed range. You pick a random array entry. You either exchange the value or you time out. And the timeout is done as an exception. So push tries to push. If it fails, you back off, visit the elimination array, and so on. Pop leaves, and if you do the exchange, and you get back the wrong kind of node. So if I'm pushing and I get back a pushing node, then I have to go back and do it again. And so on. Okay, so here is the takeaway for this part of the lecture. So we saw lock-based and lock-free implementations of queues and stacks. Lock-free queues are actually fairly widely used in all kinds of applications. They're often used for ready queues and operating systems. The other place where I was surprised to find that lock-free queues are very popular is in music. So if you're designing a codec, something that transforms music from one format to another, it has to respond in basically in real time. And locks introduce too much jitter. So if you go to Google Groups and you look up a lock-based queue, most of the hits you'll get will be on alt music, this, that, and the other thing. So anything where you need to sort of consume things in real time, lock-free queues are very popular. And in fact, the particular lock-free queue that we did here, which is due to Michael Scott and Maged Michael, is the one that most of them use. We also looked at lock-free stacks. You can argue about whether stacks are, really lie at the heart of modern computer industry, but we did that because this elimination principle is useful in a lot of other contexts. But mostly, I wanted to impress on you the fact that something that looks like it's totally sequential isn't necessarily going to be sequential. So I guess in the 15 minutes remaining, I'm going to do one last very quick thing, which is one way to do concurrent counting. So I'm going to be very quick here. But imagine that I want to implement a container, like a stack or a queue, except that I don't really care much about the order in which things are added and removed. And so what I could do is I could put a lock on the whole thing, but that lock becomes a hotspot. So what I could do instead was I could say, well, let's have a shared counter, where the enqueuer takes a value from the counter, dequeuer takes a value from the counter, and all the enqueuers share a counter, and all the dequeuers share a counter, and I won't worry about wraparound and things like that for here. But this means that only the counters are sequential. So instead of having one hotspot, I now have two, and having two hotspots is better than having one hotspot, of course. And so shared counter says that the threads come in and they ask for counter values, and they get counters, they get values. And the first thing we say is, well, we want no duplication. So we want to make sure that the same value isn't handed out twice, and there's no gaps. But we don't care whether it's linearizable, it turns out. So what we want to do is want to build a shared counter with low memory contention and lots of parallelism. So let me give you, here's a very simple gadget called a balancer. So, really, this is a shared memory data structure, but let's think about it as if it were some kind of a network. So we have two wires coming in, two wires coming out, and we have a very simple switch which points to one of the output wires. And a token, which you can think of as a message, comes in. It visits the balancer. It goes through the wire pointed to by the arrow, and it flips the switch to the next arrow. And then another token comes in. It does the same. And this keeps going. And what's interesting here is the distribution of input tokens can be arbitrary, but the output is balanced. And we'll define a quiescent state to be one where all the tokens in the network have gone through. So let's build a network of these things. So we'll call this a smoothing network, because when the tokens go through, the number of tokens that come out on the output wires differ by at most one. We'll call it a counting network if all the excess tokens are pushed up to the top wires. So the output has what's called the step property. And the reason counting networks count is that I can take a bunch of counters implemented any way you want, put a counting network in front of them, and it does a kind of a load balancing. So each counter here counts by 4, but each counter has 1/4 the load that it had before. And in here, there's no single hotspot. So all of the synchronization is smeared out over the memory. And the step property, if you think about it, guarantees that the values that are coming out, that every value is accounted for in a quiescent state. I'll skip some of the subtleties. So this is good for counting the number of networks, low contention, high throughput. Practical networks are basically log squared n, where n is the number of input wires. So this is what a counting network looks like in practice. When you come out, you take each value. This is a sequential execution where the tokens go through one at a time. This is as a particular structure called the bitonic counting network, where k is the number of input wires. And it has the property that if they go through concurrently, it's equivalent to a sequential execution. It's not linearizable. So here's an example of a non-linearizable execution. So this thread, or this token goes through. It falls asleep in the middle. Another token comes in. It falls asleep partway through. The red token comes in, and it takes 2, because the values 0 and 1 would have been taken by these tokens that are asleep. And if I wake them up and send them through now, they'll take 0 and 1. And so the counting is OK. But now the yellow token comes in, and it takes 0, which is not linearizable because yellow started before yellow started after red finished. So red should have taken an earlier value, but that's not what happened. So these things are not linearizable, but they do. It's what we call quiescently consistent, meaning that if you push if you drain all the tokens out of the network, then all the values are taken. So how do you build these things? Well, there's an inductive structure. So we take two half-size bitonic networks. We link them up to a merger network. This is what the bitonic 4 looks like. This is a half-size bitonic network consisting of a single node. This is a half-size consisting of a single node. And that's the merger 4 network. This is what the bitonic 8 looks like. Here we have 2 copies of the 4-wide. This is the merger network. We can unfold this. So here we have and in fact, it's mergers all the way down once we unfold it. This is the depth, basically a log squared k. How do we know this works? Well, let's argue by induction. So a single balancer has the step property by definition. What we want to show for the proof is that if If a k-wire bitonic network has a step property, so does a 2k merge value. By induction hypothesis, each of the half-size networks have the step property. We feed it into the merger network, and what we need to prove is that the output has the step property. The merger network is also recursively defined. We take two half-size mergers and we add one more layer. By the way, if you could figure out how to get rid of that layer, you would have a log-depth network, which is, it's known that log-depth networks exist, but nobody's ever actually constructed one. So that would be, you could get a Gödel Prize if you could prove that. This is what it looks like when you actually lay it out. The schematic is kind of conceptual simplification. So basically what we do, point out if sequence has a step property, so does its even subsequence and its odd subsequence. And so if we take two of these things and we take the even subsequence and odd and even subsequence and put them here, we now have four outputs with the step property. They differ by most one. Oops. So here the outputs have the step property. We mix them up, put them through the merger network, and we end up with each half-size merger network works by the induction hypothesis. So we have outputs here that have the step property and they differ by at most one, but it could be that the extra one is on the wrong side. So here, for example, we want this to be upstairs, so we put one more level of things, and that moves everything up. So I realize this is much too fast to follow in detail, but I just wanted to show you that this is something else that you can do. There's something called a periodic counting network, which has a completely different structure but does the same thing. And that also has a nice recursive structure. Schematically, it looks like this. And what we do is we can take a logarithmic number of these things, and that's a counting network. So this has the advantage that, unlike the other one, which was had more structure, here we have to take the same thing and we just repeat it a certain number of times. And you can prove that that's a counting network as well. Let's see. I think you can prove that if a network is a counting network, if the tokens go through one at a time, then it's a counting network if they go through concurrently. So that simplifies proving things. They actually perform quite well in practice. The way to understand it is that you think of the tokens going through as something like oil in a pipeline. If the network is too big and you have not enough tokens, then you have bubbles. If it's saturated, then you have optimal throughput. If you have too many tokens, then you start getting contention on the different switches. And so optimal performance, the number of tokens is roughly W log W. And experimentally, that has been confirmed. Okay, well, there's more other related data structures, but I won't go into that. I just wanted to alert you that there's a whole field of data structures that have this kind of flavor. And this is something where there was a lot of work on this in the 90s. It was kind of quiet for a while, and now it's picking up again because these things work well for NUMA architectures. And you can also do this in a distributed way in a lot of kind of interesting ways that reflect the realities of emerging computer architectures. Okay, so in conclusion, what I wanted to do was emphasize first off that your correctness condition matters. The fact that we can get away with all of these wild tricks is excused by the fact that we picked linearizability as our correctness condition. If we hadn't been clear about what our correctness condition was, then it would not have been obvious whether all of these fancy tricks that we do were correct or not. We wouldn't know whether it was acceptable to do all of these things. But because we started out with a good theoretical foundation, we know that we can get away with all these practical kinds of tricks. There's a lot of other data structures, hash tables, and so on. Some of those are covered in the book. Some of them are still research areas. So if you can do a really scalable priority queue, then that would certainly be a publishable result. Scalable balanced trees are hard because rebalancing is a global operation, and doing that concurrently with other operations is something that's still not well understood. So there are a lot of open questions in this area. So it's not all settled material, no matter how much it looks like it's all been done. So I encourage you to go off and look in this area, and if you have any questions, I'm here.